Hello class, welcome back. It's me, Professor Hunter. Today I'm going to be talking about chapter 2, and chapter 2 is going to be all about Newton's laws of motion, right? So just to remind you, in chapter 1, we talked about motion, and we talked about how the different viewpoints of Galileo and Aristotle, where Aristotle was the father of logic and Galileo was the father of experiment. And through experiment, Galileo was able to disprove some of these beliefs that Aristotle had. And we also talked about velocity, acceleration, and what else? We talked about velocity, acceleration, and forces a little bit, right? And we talked about how those three things are all vectors, right? How a vector is basically just some arrow pointing in some direction. And we talked a little bit about inertia, and we talked a little bit about objects in free fall, right? So just to build on the previous lesson, if you pull up the PowerPoint for chapter 2, I'm just going to be kind of going through that PowerPoint and adding in my own thoughts and explaining things here and there, so that PowerPoint will maybe make a little bit more sense. All right. So basically, let's start with Newton's laws of motion, right? So Newton has 3 laws of motion. I'm just going to give you all 3 laws of motion right here. And then I'm going to get into each one as the video progresses. So Newton's first law is his law of inertia. Law of inertia, I-N-E-R-T-I-A. All right, Newton's second law basically is force. Force is related to mass times the acceleration of an object. Or better yet, let me write it like this. Acceleration is equal to the force divided by the mass. Let's write it like that. And the third law is every action has an equal opposite reaction. You might have heard that one before. Every action has equal opposite reaction. Boom. So those are Newton's 3 laws of motion. So throughout this video, I'm just going to talk about each one of these laws, where the first one is the law of inertia, where inertia is basically related to the mass, right? And inertia basically tells you how much something is going to resist change. The second law relates acceleration and force. So every acceleration here is caused by some force. And then the third law is every action or every force has an equal opposite force. So let's first start with the law of inertia. All right, so the law of inertia. We talked a little bit about inertia with Galileo, right? So let's see, the law of inertia. Boom. So the law of inertia, how Newton put it was, how he put it in words was, any object in rest or in motion, let me write it that way, any object in rest or in constant motion, will remain in that state until acted on by an outside force. Let's see, outside force. Boom. So this is the law of inertia kind of put into words. And so any object will remain in rest or in constant motion, any object in rest or in constant motion will remain in that state, either being in rest or in motion. It's going to stay in that state until acted on by some outside force, right? And so this goes back to the old, if we push a block on some ice, that block is going to continue to slide on that ice forever until some outside force basically stops the ice from moving, or some outside force pushes the block some more and makes it go even faster. Let's see, a quick example of inertia is the old tablecloth trick. So let's say I have this cup here, this mug, pretty big mug, kind of heavy. And let's say also I have something small. Let's see if I have something small around here. Let's say this dice. Boom. This dice kind of small. So obviously this cup is way heavier than this dice. So since this cup is more massive, this cup has more inertia. So since it has more inertia, it's going to resist change more. And so let's see if I can prove that to you, the old tablecloth trick. So if I put this piece of paper here, put the cup on top of it. Now, once I slide this piece of paper, try to pull it out from underneath, since the cup has so much inertia or so much mass, it's going to basically resist the change from the paper and kind of remain in place. So let's see what happens. Ooh, okay, see, it didn't move that much. It moved a little bit, but for the most part, because the cup was so heavy, it was able to remain in place. If I were to put some water into this cup and try it again, it'd probably stay in place even more. So now let's try that same thing with this little dice here, this little die. Obviously, this little die has less mass than the cup just now. So it's going to have less inertia, which means it's going to have less of an ability to resist change. So let me try to swipe the paper. See how the dice still kind of stood in place, but it moved a lot more than what the cup did. See? Boom. So that's just kind of a visual representation of inertia. So that's Newton's first law. Let's see, looking at the PowerPoint here. Oh, here's a good example. So on the PowerPoint, one of the questions talks about, let's say this is you here, and you have some rope that you're spinning. Actually, let me draw it like this. Let's say this is you here, that's your head. And then you're swinging some rope around. This rope has like a ball on the end of it. So this is you. All right, it's like your head. We're looking down on you. And you're swinging this ball around in some circular motion. Boom, like that. So you swing it around, let's say, going that direction. So you swing it around, it goes around, so like once it reaches over here, it's going to be going in that direction. Once it gets here, it's going to be going this direction, so on and so on. Now, when you cut, let's say you're swinging it around and you cut this string here, boom, string snaps. Is the ball going to continue to go in a circle, or is it going to fly off straight? Right, so it's actually going to continue straight. It's not going to continue in its same circular path. And the reason why it's going to continue straight, let's say it's snapped over here, then it will continue straight downwards. Or if it's snapped right here, then it will continue straight to the right. It's going to continue in that straight direction because this ball here has some mass or some inertia. And so basically it's going to want to remain in this state here, going in that direction. right, so now let's see. Now let's go ahead and get into Newton's second law. If you're looking at the PowerPoint, they go through a few more examples, but I don't think those other examples are as, I don't think they're too difficult. I think with a little bit of thought, you can kind of work your way through them. So now let's go over Newton's second law. So Newton's second law. All right. Newton's second law basically relates acceleration with force, saying that acceleration is produced by force, right? And basically, acceleration is produced by force through this equation here. Acceleration is equal to the force imposed, so the push or the pull, divided by the mass, m for mass, of the object that you're pushing or pulling. So again, A for acceleration, F for force, and m for mass. So let's say, so we have a block here, right? And we push on it this way with some force F, and this block has some mass M. Let's say the mass is 5 kilograms. Let's say you push on it with the force of, let's say, 5 newtons. Remember, we measure force in units of newtons. So if you push on this block, this 5 kilogram block, with 5 newtons of force, how fast is it going to accelerate? Well, using Newton's second law here, all we have to do is divide the force by the mass. So taking 5 divided by 5, it's going to give us an acceleration of 1 meter per second. Boom. Now let's say instead of pushing it with the force of 10 or 5, let's say we double the force, and we now push it with the force of 10. Now, what's the acceleration going to be? Well, now we're going to do 10 divided by 5. So now the acceleration is going to be 2 meters per second squared. Did I do meters per second squared a second ago? I don't know. Yeah, so notice how when we doubled the force, the acceleration also doubled. All right? So now let's say now we go back to 5. Let's go back to pushing it to 5 newtons. Now let's say we double the mass. So now the mass is 10 kilograms instead of 5 kilograms. So now what's the acceleration going to be? Well, now it's going to be 5 divided by 10, right, which is just now going to be a half meters per second squared. And so notice when we increase the mass, the acceleration decreases, but when we increase the force, the acceleration increases. Did I say that right? Let me say that again. When we increase the mass, the acceleration decreases. When we increase the force, the acceleration also increases. So let me write that down. So I'm writing like this. If we increase the force, then the acceleration will also increase. If we increase the mass, then the acceleration will decrease, right? That makes sense. Because if something is more heavy and you're pushing it with the same force, then its acceleration is gonna be less, right? So I think that makes a little bit of sense, right? Now let's see what's next. Looking at this PowerPoint here. And so basically, if you double the force, you double the acceleration. If you triple the force, you triple the acceleration, and so on and so on. And then let's say you increase the mass by 2, then that's going to decrease the acceleration by a half, if that makes sense. So if you increase the mass by 3 times, then that's going to decrease the acceleration by a third. Or if you increase the mass by 4 times, then that's going to decrease the acceleration by 1/4. So now let's go back to the free fall situation, right? Where an object is falling straight downwards. Let me put that equation back up here, where acceleration is equal to some force divided by mass. So we already talked about how if we drop 2 objects of different mass, so let's say we have this object here, and it has a mass of 10 kilograms. And then say we have this other object over here, a smaller one. This one has a mass of 1 kilogram. Here's the ground. So we drop both of these masses. So we're holding them here, then we drop them both at the same time, and then they begin to fall down. So this is what we call free fall. Free fall, right? Free fall. So whenever an object is in free fall, we know it's going to accelerate downwards with what? It's going to accelerate downwards due to gravity. And we know the acceleration for gravity that we'll label as g is equal to 10 meters per second squared. All right? Now we know that they're both going to hit the ground at the same time. So both of these blocks have the same acceleration, right? But let's prove that using Newton's second law. And so basically the acceleration on these blocks here is caused by the force of gravity. So the acceleration is caused by force of gravity. I'll write that here, acceleration caused by force of gravity. Boom, right? And the force of gravity, you can write it this way, F for force with a little g for gravity is equal to the mass times g here. Boom. So each one of these has the force of gravity here pulling them downwards. So this one has a force of gravity, and then this one has also a force of gravity. But notice how I drew this force here a little bit longer than this force here. Why do you think that is? Well, let me write out what the force of gravity is on both of those. Here, the force of gravity on this 10 kilogram block is going to be the mass, right, which is 10. The mass times g, which is also 10. So the force of gravity on this block is going to be 100 newtons. The force of gravity on this block is going to be equal to what? Well, the mass is 1 kilogram. So the mass times g. So that's just going to be 10 newtons. Boom, like that, right? So we see that the heavier box here, the heavier block, is actually going to have a greater force of gravity acting on it, whereas a smaller box is going to have a less force of gravity acting on it. Right? So now let's find the acceleration for both of those boxes using our Newton's second law here, because we now know the force F, which is going to be the force of gravity, because the force of gravity is what's pulling both of these boxes down. So for this first one, the acceleration is going to be equal to the force of gravity. So it's going to be 100 newtons divided by the mass of this block. So it's going to be 100 newtons divided by the mass of this block, which is 10. All right, so that's going to give us, let's see, what's that going to give us? 10. So its acceleration is going to be 10. Let's do the same thing for this block here. So for this block, its acceleration is going to be what? The force acting on this block, the force of gravity, which is 10, divided by the mass of this block, which is 1. So dividing that, boom, we get 10. So notice the force of gravity is different on both of these boxes because the force of gravity is dependent on the mass of whatever object that we're talking about. But then notice that the acceleration for both those boxes are the same. So the acceleration is actually 10, which is actually how fast gravity is accelerating them downwards, right? And so basically that just proves that objects of different masses will always fall with the same acceleration. And so I could have done this with any numbers here for the masses. This could have been 100 kilograms. This could have been 0.0001 kilogram. The acceleration still would have been the same for both of them. But the force of gravity would have been different because the force of gravity, the Fg of force of gravity, depends on the mass of the object. But the acceleration is always going to be the same for every object that's falling in free fall, meaning that we are ignoring outside forces like air resistance or the wind blowing or anything like that. All right, so let's see what's next on the slide. So looks like they asked us a question about acceleration. Let me go over that real quickly. Let's say we have an object that is falling straight down. Boom, like so. And let's say it starts at rest. So it starts at rest. Starts at rest because we're holding it up here. And we just let it go and it falls down here. Initially, at the very, very beginning, since it starts at rest, the velocity is 0. Velocity equals 0. That's at the beginning. When it's at rest, velocity is 0. 1 second later, just 1 second, how fast will this block be falling? Well, 1 second later, since we know the acceleration is equal to g, because it's in free fall, it's going to be 10 meters per second squared. And so 1 second later, now the velocity is going to be, I'm going to write a little 1 right there for 1 second later. It's going to be 10 meters per second. So now what about 2 seconds later? So from 0, now 2 seconds later, how fast will the block be going? Right, so it's actually going to be going 20 meters per second. What about 3 seconds later? Well, now it's going to be going 30 meters per second. So notice how basically the velocity is steadily increasing, right? It's increasing by increments of 10 because it's accelerating 10 meters per second. So for every second, the velocity is going to increase by 10 meters per second. So that's basically what the 10 meters per second mean, or meters per second squared. All right. Okay. So let's see what's next on the slideshow here. Okay, so looks like let's next talk about, let's go ahead and go into, well, it looks like now they're talking about parachutes. So we're still on Newton's second law here, but now we're in a situation where something is not in free fall. So this is still Newton's second law. Write it up here, Newton's. Still talking about Newton's second law, but now we're talking about when it's non-free fall scenario. Non-free fall. Free. So any scenario where the when an object is falling and it's non-free fall, that means we're considering the other forces that are in play, like air resistance and wind and etc. So whenever an object is in non-free fall, the acceleration is going to be acceleration. Oops, spelled that wrong. Acceleration is gonna, let's just say is less than g equals 10 meter per second squared. So whenever an object is in non-free fall, the acceleration is going to be less than 10 meters per second squared, right? So let's get a scenario in mind so that this can begin to make a little sense. So let's say you hop out of a helicopter, right? Or hop out of an airplane or something like that. So let's see. Boom, that's our airplane, right? So let's say you hop out of this airplane. So you hop out of this airplane. You're falling, and then you pull your parachute. That's my parachute. Boom. So jump out this plane, and now you're falling and you have your parachute open. So the whole point of releasing your parachute is to stop you from accelerating towards the ground. Or in other words, the parachute is to prevent you from basically speeding up as you fall downwards. Because the longer you fall, the faster you start the fall, right? As we've just seen for an object that's in free fall. But now that your parachute is open, now you're in a non-free fall scenario, because now we have, the force of gravity. We have the force of gravity now pulling you downwards. Now you also have an upwards force pulling you upwards now. Let's just call that air resistance. Air Let's call it resist for short, resistance. So basically air is getting caught up underneath your parachute there, and it's pushing your parachute upwards while your body or your weight or the force of gravity acting on you is pulling you downwards. All right? And so basically these two forces here are going to cancel each other out. So whatever your force of gravity is, it's going to be canceled out by the air resistance pulling upwards. And so let me write that out in like equation form. So the sum of the forces, or the net force acting on you now, will be 0. So remember, the sum of the forces written like that, it's going to be equal to air resistance going upwards. Let's write that as FA for air resistance. So it's going to be FA minus the force of gravity pulling you downwards, right? FG. And those two forces are going to basically balance each other out, putting you in, boom, putting you in, what do we call that? We call this dynamic equilibrium, right? So you're falling down now at some constant speed because the air resistance and the force are going to cancel each other out. And whenever the sum of the forces are equal to 0, but you're still in motion, we call that dynamic equilibrium. Versus when we just have an object just sitting there like this, that's just in regular equilibrium. But anything moving with a constant velocity is in dynamic equilibrium. So you open up your parachute. So let's say you're falling, you know, you're falling fast. You pull open your parachute and then you start to kind of just float downwards at a constant velocity. So let's see. So now let's do a non-free fall scenario outside of the parachute. If you're looking at the PowerPoint, they have an example up, and it says when a 20 Newton object encounters 5 Newtons of air resistance, its acceleration of fall is what? Well, let me work that out here. So basically it's saying that we have some object here, and it's falling down with a force of 20 Newtons. And that must be the force of gravity, 20 Newtons. And then the air resistance, because there's air, you know, basically everywhere, like that. And the air is pushing upwards as it falls down. This way, let's make it a little smaller, because the air is not actually resisting that much, but it is resisting by some amount. And that's, let's call that FA for air resistance. It's pushing upwards with 5 Newtons. Boom. So the question is, how fast is this block accelerating downwards, right? Well, if we do the sum of the forces on this block, that's going to be the force of the air resistance, which is 5 upwards. All right, and then minus gravity, because it's pulling opposite in the opposite direction by 20. So minus 20. And so now the net force here, is going to be, what's that going to be? The net force is going to be negative 15 Newtons. All right, and so what is the question as? It's acceleration. So we want the acceleration, right? And this is just the net force. And notice that the net force is negative here. We don't have to worry too much about this negative. This negative just means that the total force is basically downwards. We usually consider downwards to be the negative direction. So now we know from Newton's second law here that A, or the acceleration, is equal to force divided by mass. And so we're trying to find that this acceleration here, but we do not know what the mass is. In the question, they only give us the force of gravity, which is 20 newtons. Well, we actually know from this we can figure out the mass from this, because we know the force of gravity is equal to mass times the acceleration due to gravity, right? So this 20 newtons is equal to mass times the acceleration due to gravity. And we know that's 10 meters per second. So let me just erase that and make it a 10. Boom. So take this 10, divide it over here, and actually solve for what that mass is. So taking 10, dividing it over, we see that the mass is equal to, what is that, 2 kilograms. Boom. So now we can figure out what the acceleration is. So if we take basically this 15, because it's going to be the sum of the forces that go on the top here, acting on this block, and divide it by 2. Well, what's that going to give us? So that's going to be A equals, I'm just going to ignore that negative for now. Remember, the negative just means that it's being pulled downwards. So it's just going to be 15 divided by 2. So the acceleration is, well, what's 15 divided by 2? I think that is 7.5. 7.5 basically meters per second squared. Boom. So this is an object falling in non-free fall, and notice the acceleration is less than how fast an object would fall in free fall. Because if it were in free fall, it would fall at 10 meters per second. That's supposed to be squared. But since there's air around here, so some air resistance of 5 newtons, the acceleration is only going to be 7.5, right? So the acceleration is going to be less than g. So now let's see. So now let's talk about what terminal speed is, because I see that they use that word on the PowerPoint here. So this goes back to the this is basically another non-free fall scenario. So we're still talking about non-free fall. And let me just talk briefly about what terminal speed is. Terminal speed. Terminal speed is basically your, how do you say, it's going to be the maximum speed that you reach when you're falling downwards. So this is going to be your max speed. Your max speed as falling downward, I guess that makes sense, as falling downwards. So what do I mean by that? Well, in a regular free fall scenario, we said that the acceleration was equal to 10 meters per second, right? So the acceleration was equal to this, right? And as each second passed along, basically the velocity went from 0 to 10 to 20 to 30 to 40 to 50, so on and so on. But in the real natural world, your velocity actually has some limit because there is some air resistance. You know, there is these outside forces acting on you as you fall down. So if you were, let's say, inside of a vacuum or something like that, I'm not sure how you would be in a vacuum because that means there would be no air for you to breathe. But let's say you didn't have to breathe air and you're falling in a vacuum. If you're falling in a vacuum, you're basically gonna continue to speed up, you know, the longer you fall. So it goes 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, so on and so on, as each second passes on. But luckily, that doesn't happen in real life. So now let's go back to this terminal speed situation. So basically, in a non-free fall scenario, you always reach some terminal speed, which is basically gonna be like the maximum speed that you reach as you're falling down. So if we go back to the airplane scenario, all right. So let's say you jump out of this airplane. Ooh. Skydive, right? Jump out of this airplane, you start to fall downwards. So what happens is you initially jump off the airplane and you're falling, and your velocity will actually increase as you fall downwards. But then you're gonna reach the point to where you reach your terminal speed. So you're gonna fall, speeding up until you reach your terminal speed, to which then you just fall with a constant velocity. So for a non-free fall scenario, we know there's outside forces acting on you, causing you to reach basically that terminal speed. And so now let's look at the question that they have on the PowerPoint there. I think it's on slide number 35. It says if a 50 Newton person is to fall at terminal speed, air resistance is needed. Well, how much air resistance is needed? Well, when you're in terminal speed, we can actually say that terminal speed is when you reach dynamic equilibrium. Ooh, I hope I spelled that right. You know what I mean? This is when you reach dynamic equilibrium when you're at terminal speed. So that basically means the sum of the forces are going to be equal to 0, right? So if we know this person is falling with 50 newtons, the force this person is falling with is 50 newtons. How much air resistance is needed to push back in the opposite direction so that the sum of the forces are equal to 0? What do you think? Well, if you think it's 50, then you would be right. The air resistance must balance out with basically the force pulling downwards. So it must be something like this. in terminal speed, you have some air resistance minus the force of gravity. This is the force of gravity equal to 0. So the sum of the forces are going to be equal to 0 whenever you're at terminal speed. So then if I just look at this part of the equation, so this part right here, I can actually add over the force of gravity to this side, and we see that the force of the air is going to equal the force of gravity. So all that to say, if this person has a force of gravity of 50, then the air resistance must also be 50 in order for this person to reach terminal speed. All right, hope that makes a little sense. And that basically means that this person is not accelerating downwards, right? Because he's in dynamic equilibrium. So he just has a constant velocity as he falls down. And so now let me draw well, let's keep going here. Erase that. Let's see, what's next on those slides? I'm skipping a few here. Some of these I'm sure you can do yourself. All right, so let's look at slide number 44. So slide number 44, here we have two people of different masses. So they have different weights. So let's say we, on slide number 44, there's a bigger person. I guess I'll just draw him as a circle, right? This is the bigger person, and he's falling downwards. You know, there's his parachute. Let's say there's also a smaller person right here. Let's use a stick for that guy. And those parachutes are supposed to be the same size. So the question is, which person will reach the ground? Let's say this is the ground here. Can you see that? Let me do it right there. Boom. Which person will reach the ground first? Well, you might think that they both reach the ground at the same time because of the whole, you know, heavy objects and light objects falling at the same acceleration. But this is a non-free fall scenario, not a free fall scenario. If this was free fall, then of course, you know, free fall meaning we take away the parachutes and they're both just falling down. Then they would both hit the ground at the same time. But here, let's say this bigger person is falling down. Okay, so let's kind of analyze this from the beginning, right? So let's say the heavier person just jumped out of the plane. Boom. That's the heavier person. He just jumped out of a plane. He's falling downwards with, let's say 100 newtons. All right? And so as he falls downwards, his acceleration is going to be decreasing because of the air resistance, right? So he's falling downwards. He's falling down. But since this person is heavier or bigger, it's going to take more air resistance to basically, or for him to reach dynamic equilibrium. So if I were to draw his vector or his force down this way, we know that the air resistance upwards is going to be by the same amount. right? So that the force of gravity and the air resistance cancel each other out. Similarly, this person's going to have some force of gravity pulling downwards, and the air resistance, basically balancing out upwards. Should be about the same size. Boom. So notice, basically, this heavier person is going to have a greater terminal speed than this lighter person. Why? Because this person, or this heavier person requires more air resistance to basically balance him out. Let's see if I can explain that a little better. Let's see. Let's think about it like this. So as soon as this heavier person pulls out their parachute, it's going to be harder for the parachute to slow this person down because they have more mass than this person. They're both going to reach some terminal speed, but this person's terminal speed is going to be greater than the lighter person's terminal speed, right? Because if you think about it, if this person pulls, the lighter person pulls his parachute out, since this person's a lot lighter, the air resistance required to slow him down will not be as much. So he will not reach the same terminal speed that this person will reach. So all that just to say, the heavier person's going to reach the ground faster. And if this seems like a lot and you don't understand it yet, don't feel bad or don't feel any kind of way about it. It took roughly about 2,000 years for people to get a whole understanding of Newton's laws of motion. So there's no way you're going to get it within an hour or two. But if you do get it, then, kudos to you. But if you don't, just keep watching, do the homework, and hopefully as you go along, it'll make a little bit more sense. But if it doesn't, just remember, this is basically 2,000 years worth of information that I'm trying to, put inside of your head. So now, let's get into Newton's third law, the very last one. Newton's third law is Newton's third law is what is it? Every action, so action equals, let me just write it this way, shorthand, equals every action equals, well, let me say every action has equal opposite reaction. Boom. And that's Newton's third law. Every action has an equal opposite reaction. So what do we mean by that? Well, in order to explain this a little better, let's think of forces as interactions, right? So let's say, you reach out and touch somebody. Well, you can't necessarily touch somebody without, them touching you back, so to say. So like if you touch somebody, like you've touched somebody's hand, their hand is also touching you back, right? Or I guess a better example would be if you push on a wall, basically the wall is going to push back on you because the wall isn't going anywhere. And so basically for every one interaction, let's think about it like this. For every one interaction, for every one interaction, there's two forces, two equal but opposite forces, right? So for every interaction, there's two equal opposite forces, all right? So let's think about, let's go to the, let's say you're pushing on a wall scenario. So let's say here's a wall here, boom. And let's see, here you are trying to push on the wall. And this is a wall, right? You can't move it. The wall is just gonna stay there. And you're pushing on this wall this way as hard as you can, let's say with a force of 50 newtons. So you pushing on this ball, or this wall, you pushing on this wall is the one interaction. And so there must be two forces, right, of equal opposite direction. There's this force that you're pushing of 50 newtons that way. So the wall, since the wall's not moving, must be pushing back on you. The wall must be pushing back on you this way. It's supposed to be the same length. Of 50 newtons. All right. So if we were to call, this person A, let's call this person A. So person A pushes a force of 50 newtons on wall B. So let's write it like this. Person A pushes 50 newtons on wall B. And I'm gonna use blue, and let's say the wall is B, right? And so the equal opposite reactionary force would be, well, the wall, which is be pushing a force of 50 newtons on A. So the wall would be B, basically pushing back on A. Boom. So I hope that makes a little bit of sense. Let's look through the PowerPoint here. Blah, 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 blah. They use the wall scenario. Okay, so let's let me give you another scenario where this isn't too obvious. Let's do the Earth and the Moon, right? Two things that have different masses. Because here, it's not too obvious that this equal but opposite force law is in play. So let's say over here, we have the Earth, big and blue. And let's say got the moon over here, small and dark. So we know, well, you may not know, but people usually say that the moon is pulling on the Earth, right? The moon is pulling on the Earth, and that's what causes basically the tides in the ocean, right? So now my question to you would be, if the moon is pulling on the Earth, is the Earth also pulling on the moon? And if so, which one is pulling more? Right? Let's see. Well, they actually pull on each other with the exact same equal but opposite force. All right? So remember I said every one interaction has two forces of equal opposite, going in opposite directions. So the moon and the Earth, that's one interaction. And so there must be two forces pulling at both the moon and the earth, equal and opposite in direction. Now, I could explain that using equations and etc., putting in numbers and doing all that. But for the most part, you just need to understand that they basically pull on each other with the same force. You can kind of imagine it's like if I had a rubber band. Let's see, I don't have a rubber band, but let's use this mask here that I have. So if I put this mask on either one of my fingers, let's say I leave this finger here and I pull the other way with my other finger. It's kind of the same scenario as the Earth and the Moon. The question within would be, well, which finger is pulling with more force? Well, actually, the force on both of my fingers are equal and opposite in direction. So this finger, on this finger, the force is pulling that way. But for this finger, the force is pulling that way. So equal forces, but in opposite directions, right? And now let me give you another scenario of equal opposite forces. Let's say there's a piece of paper, right? Say you have a piece of paper here. All right. So got this piece of paper here. Now let's say you walk up to the strongest person you know, the strongest person, biggest, toughest guy, and you bring this piece of paper to him and you tell him, I bet you $100 you cannot hit this piece of paper with 50 newtons of force. So, it's supposed to be a hand. So you say you cannot hit this piece of paper with 50 newtons of force, right? And then, of course, he laughs, ha ha ha, I bet that I can. He attempts to do it and come to find out he cannot hit this paper with 50 newtons of force. Why can he not hit this paper with 50 newtons of force? Well, again, this hand applying a force on this paper is one interaction, right? So then there must be two forces. So the force from the hand hitting the paper, then a force from the paper actually hitting back on the hand. Now we see basically this hand or this piece of paper has obviously a very, very, very small mass, while this guy's hand may weigh, a couple kilograms or more. So basically, he cannot hit this paper any more than what this paper can hit back on his hand, because this paper is small. This paper doesn't weigh that much, so this paper cannot apply that great of a force on his hand, even though his hand can probably, supply a great amount of force. But since this paper cannot hit back with that same amount of force, he cannot hit that paper with any amount of force. Does that make sense? I'm not sure. Let me give you another scenario, and maybe that'll make a little bit more sense. Well, I can't think of a scenario now. I was going to do the punching bag scenario. Yeah, let's go with the punching bag scenario. So let's say you have a punching bag. There's two of them. Got this punching bag. Let's say we got this really big punching bag. Right? Got two punching bags, and we got this guy here. Same guy. And he's got his gloves on. He's ready to box. Boom. This is huge. And let's say let's say this bag is actually hollow, so there's nothing on the inside. It's empty. Let's say it's empty. I don't know. That's how I draw empty. And this one's full. Just draw lines on it. Right? So if this guy punches both of these bags with the same amount of force, which one can, well, I guess my question to you would be, which punching bag can punch back on him harder? Well, since this punching bag is hollow, this punching bag is basically not that massive. So the mass of this punching bag is very, very low. So he can punch this punching bag and it'll have some limit. Whereas he can hit this punching bag, probably as hard as he really wants because it's so heavy. And this punching bag can basically supply back a greater amount of force because it has a greater mass. All right, so now let's go move on to the next scenario. Let's do a couple other scenarios. Let's say you're standing on some ice. Right, this is you standing on some ice. And let's say you're standing on this ice and you want to go this way, you want to go that way. You want to go that way. So you want to go towards the left. So how can you go towards the left without actually walking, right? Because if you walk on this ice, you might slip and fall. Let's say this is the ice, slippery. If you try to walk, you might actually slip and fall. So how can you actually go in this direction without walking? And let's say you have a brick in your hand. So you have a brick, boom, just like that in your hand. So if you want to go towards the left, you can actually throw this brick to the right. If you throw it this way, all right? And so you throwing this brick, that's basically one interaction, right? And so there must be an equal opposite force pointing in the opposite direction, right? Because for every one interaction, there's two equal opposite forces. So the amount of force that you push on, or that you throw this brick with, will then propel you towards this direction. And it's going to propel you in that direction because basically there's no friction on this ice to hold you back. So now let's do one more scenario, kind of like this. So now let's say let's say there's another guy here. I'll do him in red. That's the other guy. And let's say you guys basically push off on each other. So if we both push off on each other, we know y'all are both gonna push each other with the same force, right? So if you push him, you know, he is essentially pushing you, you know, back in the opposite direction. And so now my question to you would be, who is going to accelerate faster? Well, let's put some numbers to it. Let's say you guys push on each other with the force of, let's say, I'll write it right here, a force of 50 newtons. That's how much the force is y'all push on each other. Now, let's say this person has a mass. This person has a mass of, let's go with 50 kilograms. And then this person is half of that. He has a mass of 25 kilograms. So who do you think's gonna have a greater acceleration in these opposite directions? Because we know he's gonna accelerate that way, and this guy's gonna accelerate the other way. Well, we know from Newton's second law, right, that we can find the acceleration with what? A equals the force divided by the mass. And so they both experience the same force in opposite directions. So let me use black for the force arrow. So he's gonna feel a force that way, and he's gonna feel a force that way. And notice I drew those black arrows the same size, or I tried to. Supposed to be the same size. So the black arrows are for the acceleration. But then also notice that I drew this blue and this red arrow. I drew those for the acceleration. So now let's solve for the acceleration for both of those. So for this guy in the blue, his acceleration is going to be the force of 50 divided by his mass of 25. So 50 over 25. Well, his acceleration is going to be 2 meters per second squared. Boom. And so for this heavier guy, his acceleration is going to be what? 50 divided by 50. So that's just going to be 1 meter per second squared. Boom. So that's why I drew this blue acceleration arrow bigger, because since this guy is smaller, even though they push on each other with the same force, he's going to go this way with the greater acceleration, while the heavier guy is going to go to the left with less of an acceleration. All right, I hope that makes some sense. And that's just about it. Just looking through the slideshow here, or the PowerPoint, and they go through a few more examples, which I'm pretty sure you can go through on your own. Okay, so the last thing I'm gonna discuss then is lab number 2. We'll discuss a little bit about lab number 2. So if you go into Blackboard and go into the lessons and assignments tab for week 2, you'll find lab 2 there. And lab 2 is called torque. I know we haven't talked about torque yet, but I'm gonna give you a quick rundown here, so hopefully you can understand that lab. So first, torque is basically what happens when you apply a force to something and that object begins to spin. So if I have this eraser here, and I apply a force on this end, it's gonna begin to twist around, and then that twist around is what we call the torque, okay? And we usually use this weird looking T for torque there. And so the torque is equal to R for radius, times what? F, the force. And so just keep that in mind, where R equals the radius and F is for force. So now, in the lab, you're gonna have some scenario like this, basically a seesaw. And this seesaw is just balancing there, right? And so we then, once you go through the lab, you'll be putting different objects of different masses on either side of this seesaw. So obviously, if I were to put a block over here on this side, then the seesaw would want to basically fall in that direction like so. And that's the torque that we're talking about. Similarly, if I were to put the block over here or something, then it would want to fall in that direction. So now, if I take two blocks of the same mass and put them here and here, then what would happen? Well, nothing, right? Because the seesaw would balance itself out here. Yeah, so the seesaw would balance itself out. So now, let me use this scenario and describe how we use this equation here. So starting from the middle or the center, we go from the center and measure in either direction to the mass that we're talking about. So from here to here, that's the R. And then the force is going to be the force of this block pulling downwards. So it's going to be the mass times acceleration, or the mass times acceleration of gravity. So this is pulling downwards, right? With the force of gravity, that's equal to mass times gravity. Same thing for this block over here, Boom. So basically, this here is R and the force here is mg. So our torque then is going to can be basically R times m times g. This is important. This is going to be the key to your lab here. This is going to be the key to your lab. Can't stress it enough. Key to your lab. You're going to use this here. So now, since both of these blocks are on here and the seesaw isn't moving, the seesaw is in equilibrium, right? So that means the sum of the forces for this seesaw is equal to 0. But in this case, since there's torques, or T for torques, happening on this seesaw, it's going to be the sum of the torques are equal to 0. So in order for the seesaw to balance, so for balance, the sum of the torques have to equal 0. That's key. So each one of these masses are causing a torque, right? So the torque from this mass must balance out with the torque from this mass to give us a sum of torques to be 0 so that the seesaw balances. So now in your lab, you're basically going to be using different masses and placing them at different places on this seesaw, trying to get the seesaw to balance out. And then you're going to be asked to find the mass of some of these objects. And so let me do a quick example here of how that's going to work. And let me put tick marks on here. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 1, 2, 3, 4. That's at 5. 1, 2, 3, 4. It's at 5. So now let's say I put a block here that is on 5. And the mass of that block is 5 kilograms. 5 kilograms. Now let's say I put another block right, boom. Let's say here at 1, 2. Right here. Make it smaller. Boom. And it's at placement of 2. So in your lab, they're going to ask you, well, in order for this seesaw to balance out, so we want the sum of the torques. You kind of think of torque as like a force. So you want the sum of the torques to be equal to 0 so that it's in equilibrium. Then what does the mass of this block have to be, right? So each one of these blocks are causing a torque, right? So this block is pulling downwards. This one's pulling downwards with some force of gravity, which is equal to mg. And this block is also pulling downwards with some force of gravity. It's also equal to mg. And now, since using the equation I gave you a moment ago, we know basically torque is equal to the radius, which is the distance from the center to that block, or the distance from this block to that block. That's the radius. So let me do this block first. So from here to over here, that's your radius. And that's equal to 5. So 5 meters. 5 meters. All right. And what's the rest of this equation? It's R times F, the force. And the force is mg. So the torque is going to be Rmg. So the torque that this block is applying is going to be R, which is 5, times the mass, which is also 5, times G, which is 10, right? So 5 times 5 is 25, times 5, or 5 to 5 is 25 times 10. So for this block, the torque is going to be 250. Okay. So now using this torque, how can we find the mass of this block? Well, basically the torques of both of these blocks have to cancel out, right? So the torque of this block has to equal this torque in order for this seesaw to be in equilibrium. So let me write out the torque for this blue box. It's going to be torque is equal to R times mg, right? And here R is 1, 2. So from here to here, R equals 2 meters. And we know G is 10, right? So this becomes 2 times 10 times whatever that mass is. So 2 times G, which is 20. It's gonna give me 20. And then the mass there that we do not know. We don't know this mass, but we know this torque has to be equal to this torque. So we can set these two torques equal to each other. So we can solve for the mass, right? And let's see, I'm gonna do that right over here, erase this. So setting those two equal to each other, we have 250 equals 20 divided by the mass. And so now we can solve for this mass here, this mass, the smaller block, by dividing 20 over. And so the mass is going to be equal to what? What's half of, let's see, calculator, 250 divided by 20. It's going to be 12.5. 12.5 kilograms. So if this block is placed here, in order for it to balance out, this block has to be 12.5 kilograms. So I actually should have drawn this box a little bigger. This box should have been a little bigger. It should have been, you know, bigger because it weighs more. Boom. So this is basically lab 2. If you're already finished with lab 1 and you want to get ahead and you're already looking at lab 2 and you have more questions, feel free to email me. Again, can't stress this enough. The sum of the torques have to equal 0. So if there is like more than one object on this side, so say there's another block over here on this side, then these two torques have to equal this one torque, so that they balance out. And then again, the torque is going to be given with this equation here. So your torque is going to be equal to the R, which is the radius, which is measured from the center, times the force, where the force is going to be the force of gravity, which is mg. All right. Hope that makes sense. Good luck with the lab. Good luck with the homeworks. If you're having any trouble, please feel free to email me. I hope these videos help. See you next time.